Hello, everybody. We are going to go after the most difficult yet most important property of stars in this video. We've covered a lot of the properties. We've determined a lot of them observationally, yet the most crucial, the one that's actually sort of governing the entire behavior of the star, what's going to be the thing that we measure the life and death and determines the life and death of stars, is the mass of the star. How much stuff is it made out of? How much hydrogen and helium does it have? How much hydrogen fuel does it have in its core to fuse into helium, thus causing the luminosity and causing the star to shine bright in the night sky? How can we actually determine the mass, though? This one is tricky. And yes, we have covered the basics. So hopefully you can appreciate why we spent so much time with Kepler and Newton as we go after the masses of the stars. Okay, so how do we go and get the mass of a star? There's nothing I can really look at the HR diagram that'll tell me what the mass of the star is. I can make some guesses based on physics about what stars should be more massive. It seems like the O class, the O and B stars, the hot stars, yeah, I would guess that those are the more massive stars. And then the smaller stars, the M-type stars, are the less massive ones. But how do we actually determine what the masses are to actually confirm that suspicion, that hypothesis? Well, what we can do is we can go and find binary star systems. So these are two stars, or sometimes they come in multiple systems, but typically we want to look at binaries where we have two stars in orbit around one another. We understand orbits. We went over this in Unit 1, Part 3, whenever we took Newton's laws of motion and Newtonian gravity to modify Kepler's laws of planetary motion. The benefit of Newton's modifications is that they applied anywhere in the universe. Anytime you see objects in orbit around one another, you can apply Newton's modification to Kepler's third law. So let's just remind ourselves, what is a Newton's modification to Kepler's third law? I've put it here on the screen for us to take a look at. It's that the period squared equals the semi-major axis cubed, the semi-major axis of either of these orbits, divided by the total mass of the system, the mass of one star plus the mass of the other star. And over here, I have an example of two uneven masses, then roughly circular orbits, and here I have two equal masses, then elliptical orbits. So we have a way where if we can determine the period in the semi-major axis, then we can determine the mass. I don't have enough time to go into all the hard details because it's not easy work. So you're going to have to trust me on this one. But through observations of these stars, really high precision positions of these stars, we can actually determine the period and the semi-major axis. That's really rare and kind of hard to do. So normally we rely on spectroscopic means, where we are determining the motion towards and away as these stars orbit around. So we're using things like the Doppler shift to infer what the period and semi-major axes are. It's a good bit of work, but we can do it fairly well. And we can nail down what the period is and what the semi-major axis of these binary stars are, which leaves the only thing that we don't know is the total mass, which if we can do a good job measuring the semi-major axes of each of these orbits, then we can actually break this apart and not away from the total mass to the mass of each star. So the details are a lot more complicated in the practice, but the idea is fairly simple. Go out to the telescope, find some binary stars, figure out what the orbital period is, figure out what their semi-major axes are, and then solve for the mass. And that's how we can get the masses of the stars. So all we have to do is observe as many binary systems as we can. And then as we observe more and more of these binary systems, we'll get more and more data points on the masses of the stars. And while we're at it, why don't we measure, say, the luminosity of the star and the temperature of the star using all the previous things that we've talked about. So now we can get at the mass and start correlating it and looking for patterns with the mass and other properties of the stars. All we have to do is observe these binary stars. And the process is fairly simple. Determine the orbital period, determine the semi-major axis, solve for the mass. And you might think that this is rather difficult to do. However, it's estimated about 1/3 of all the stars in the Milky Way galaxy are in binary systems. So it really is almost like just pick a star in the sky and point your telescope at it. It's probably a binary system. So yes, we can do this for a large number of stars. We can get a good number of statistics, and we can really start understanding the mass of the star and connect it to other properties. So let's just take a look. How would this compare to, say, our HR diagram where we're looking at the main sequence of stars? How does the mass of the star link to the properties of the luminosity of the stars and the temperature or spectral class of the star or color index of the star? And so we can go ahead, measure a whole bunch of binaries, and we can now see that our M-type stars, our cool red stars, really are the low mass stars. And we know that that low mass is about 20% that of the sun. Then we have our sun at one solar mass. And as you sort of tick off each spectral class, you notice that the O and B stars are roughly 10 to 20 times the mass of the sun. Every once in a while, you found some extreme outliers that are, say, 30, 50, or 100 times the mass of the sun. But those are extraordinarily rare, where there's only a handful of them that exist within our galaxy itself. So, with few exceptions, nearly all the main sequence stars, from the low mass M end to the high mass O end, are between 1 or zero point 0.1 and 20 solar masses, a tenth the mass of the sun to 20 times the mass of the sun. And that gives us a range of what the masses of stars are, and it connects them to properties. So here we're looking at the luminosity and the photospheric temperature. So we can see that the higher mass stars are brighter and have higher surface temperatures. They are, since these are in hydrostatic equilibrium, they're on the main sequence, that they are producing a lot of energy per second through fusion in their cores. And the low mass stars are not as bright. They are not converting hydrogen to helium very fast in their cores, giving them a lower luminosity, and they have a lower temperature. And more than that, besides just defining the range, it'd be good to know, like, okay, well, how many stars are less massive than the sun and how many stars are more massive than the sun? What is the distribution of masses? Are there a lot of high mass stars, or are there few low mass stars? Or, and we can go ahead and do that. This is just a graphic, but this is the breakdown of the masses of stars. And I'm not going to ask you to memorize any of these details, but I want to hit a couple of the highlights. Less than a fraction of a single percent are the hot O-type stars. So our O-type stars and our B-type stars are extraordinarily rare. Very few stars end up being high mass stars. We go to the other end of the spectrum, to our low mass end, our cool end, our M stars, our faint cool M stars, which we now know are low mass. Over 70% of all the stars are low mass M stars. And as you go up, so the most of the stars are M stars, and then you have slightly fewer K stars than G. So as you move to the hotter end of the spectral classes, you get fewer and fewer and fewer of those stars. The breakdown, comparing it to the sun, roughly 10% of the stars are more massive than our sun. So we're kind of on the high mass end of stars if you want to consider of all the stars out there. Only 10% of stars are more massive than the sun, which means 90% are less massive than the sun. So the takeaway here, what I'd like you to remember is that there are a lot more low mass stars than there are high mass stars. So there are very few O-type stars and B-type stars. There's a whole bunch of M-type stars. And now that we've figured out the masses of the stars, now we can really get into the fun stuff, and we can look at how the different properties relate. So what you can do is a typical way to do some empirical science here is we have two different properties, and we just want to go ahead and plot them against one another. We want to look at, say, the mass of a star versus the radius of a star, which we can get from the radius luminosity temperature relationship. We get our mass from binary stars. So we can go ahead and see how the stars, how these two properties relate to one another. So you can go ahead and do that, and you can see that they follow this nice linear trend. You can fit a line to them. And this shows us like what we're really seeing here is how we empirically can determine things like the mass of a star is directly proportional to the radius of the star. Or say that the other way, the radius of the star is directly proportional to the mass of the star. So in general, double the radius, double the mass. Half the radius, half the mass. Okay, so there's a connection between the mass and the radius of the star, radii of the stars. This is the really big one though. Let's take a look at the mass of the stars versus their luminosity. We can determine their absolute magnitude, convert that to a luminosity. So we can go ahead and look at that. And notice that we're now at a log-log plot. So look at that these are not evenly spaced, 5, 10, and then 10 to 20. And then the y-axis is a logarithmic axis as well, 1, 100, 10,000, 1 million. So this is a log-log plot. So whenever you plot something like this and you see you have a line and this line will have a slope to 3.5, that means that the luminosity here is proportional to the mass raised to the 3.5 power, to the exponent of 3.5. So here we see a connection between the mass and the luminosity. And we see that this connection, this correlation, is that the luminosity of a star is proportional to the mass of the star raised to the 3/2 power. So the luminosity is proportional to the mass of a star raised to the 3/2 power. Double the mass, the luminosity would go up by 2 to the 3.5 times power. And you could go ahead and do that, but I'm not going to have you do that relation. What I want to do is take this mass and luminosity relationship and apply it to come up with something that's really darn cool. Come up with how long will a star live on the main sequence. Remember, this 90% of its lifetime. So you're really talking about how long will a star live? And yes, stars live and die. Stars are not eternal. And how long a star will live for depends on the mass of the star. Because the mass of the star determines how much hydrogen fuel is there. It also determines how fast it's going to be burning up that hydrogen fuel, fusing that hydrogen into helium. So we have a amount of fuel, we have a fuel supply, and then we have the rate that we're burning the fuel at. We can use those to figure out how long a star will live. How long can it continue fusing hydrogen into helium in its core until it runs out of hydrogen? The analogy here would be you know how many miles per gallon you get in your car. You know how many gallons you have in the tank, how much hydrogen you have in the core. You know how fast you're burning that, how many gallons of gas you're using, what your miles per gallon are. So you could figure out how far you could go, how long you could travel, given the amount of fuel you have. That shouldn't surprise pretty much anybody. That's fairly intuitive. We're doing the same thing, but instead of gas in a gas tank, we're using hydrogen in the core of a star. And we're not using combustion, we're using nuclear fusion of hydrogen into helium. So let's do this same idea. So here our fuel is the amount of hydrogen that's in the core of the star, proxied by how much by the mass of the star itself. Now, how fast our miles per gallon, our rate of burning fuel, is really given by our luminosity. It's how much energy the star is emitting every second. And since the star on the main sequence is in hydrostatic equilibrium, that means that is the amount of energy being produced by nuclear reactions in the cores of these stars. So the luminosity is telling us how much energy is being produced every second. And we can calculate how much hydrogen needs to fuse to helium to produce that amount of energy. We did this with the sun. So here we have how much fuel we have, and here we have how fast we're burning the fuel. Put those ideas together, and you can calculate how long that star can live on the main sequence. And that's 90% of its life. So that's pretty much the lifetime of the star. So the lifetime of the star would equal how much fuel you have divided by how fast you're burning that fuel. So how much fuel you have in the tank, and then how fast you burn that fuel. That makes sense. It's the same sort of idea that we'd do if we wanted to calculate how far you could go on a tank of gas given your gas mileage. So the lifetime of a star is going to be proportional to the mass of the star, how much fuel you have, divided by the luminosity of the star, the rate at which you burn the fuel. But we just saw that the luminosity is proportional to the mass of the star raised to the 3.5 power. So why don't, instead of using luminosity here, why don't I just put that as mass to the 3.5 power? Then I have the lifetime only depends on the mass of the star. So we can put those two things together and we see that the lifetime is the mass divided by, oh, since the luminosity is proportional to the mass of the 3.5 power, I can go ahead and change the luminosity to mass to the 3.5 power. So mass to the first power divided by mass to the 3.5 power equals 1 divided by mass to the 2.5 power. So the lifetime of a star is inversely, so you're dividing by the mass, it's inversely proportional to the mass of the star raised to the 2.5 power. So the star's main sequence lifetime, how long a star will live, is inversely proportional to the star's mass raised to the 2.5 power. This is why we wanted to get the mass of the star, because the mass of the star determines the lifetime of the star. So now we have a way of determining the main sequence lifetime, as we call it. How long will a star live on the main sequence? So we label this the main sequence lifetime. We use, instead of t for time, we use the lowercase Greek letter tau, or ta, if you want to pronounce it more appropriately. So you have ta of main sequence lifetime. So our main sequence lifetime is proportional to 1 divided by mass to the 2.5 power. Same thing as saying that the lifetime, main sequence lifetime, is inversely proportional to the mass raised to the 2.5 power. That's great, but that's just a proportionality. What I need to do is I need to anchor this. I need to compare this to something that we know. I have to give it some sort of a standard. So we can standardize to the sun's lifetime. The sun's lifetime, and we went through this exercise in the section of the class on the sun. The sun has a lifetime. It has enough hydrogen in its core to keep fusing hydrogen into helium via the proton-proton chain for 10 billion years, 10 giga years. Giga means billion, so 10 giga years is 10 billion years. So if we want to compare everything in terms of lifetimes compared to, say, the sun, then we can use this as our standardization. And we can now rewrite our proportionality as an equation where we're getting the lifetime in giga years. So now we have the main sequence lifetime of a star equals 10 billion years divided by the mass in solar masses, because we standardize this to the sun, raised to the 2.5 power. Notice that if I plug in the mass of the sun in solar masses, I will get an answer that is the lifetime, the main sequence lifetime of the sun. Plug in one solar mass, 1 raised to the 2.5 power is still 1. So the main sequence lifetime of the sun is 10 billion years. So this equation works as long as we have our mass in solar masses. And now we can use this to reason out. Let's go to stars that have a lower mass than the sun. We make this number smaller. The main sequence lifetime is inversely proportional to the mass raised to the 2/5 power. So if the mass goes down, then the lifetime goes up. Low mass stars live longer. High mass stars, the mass goes up, the main sequence lifetime goes down. High mass stars live a short amount of time. Now, if you've been looking at this table over here, because it's extraordinarily interesting as tables go, then you can see the main sequence lifetime for different masses. So we have our M-type stars, our K-type stars, we have our G-type stars, and then we have even our O-type stars and ridiculously massive O-type stars. And you have ranging from trillions of years as their main sequence lifetime to hundreds of thousands of years. Wow. Okay. Now, yeah, I don't expect you to memorize this table, but I want to give you some practical examples so we can at least figure out how long do the highest mass stars live and so what's the shortest lifetimes we can expect and what are the longest lifetimes we can expect. With this, we'll do a couple of examples. So we have the lifetime. I want to figure out the lifetime of a 20 solar mass O-type star. About as massive as stars get, 20 solar masses. Just have to plug this number into my equation. So my main sequence lifetime is going to be 10 billion years divided by the mass of the star in solar masses raised to the 2.5 power. So 10 divided by 20 raised to the 2.5 gives me 0.0056 billion years. At that point, I don't want to use billions of years. Let's just use millions of years instead. 5.6 million years. That's cosmically fast. 5.6 million years is not a very long amount of time compared to the age of the universe. O stars are very, very, very short-lived. And B stars at about 10 solar masses are not that different. So note that that means all O and B stars, these super high luminosity, bright blue stars, are all extraordinarily young. If you see them in the sky, they recently formed, or at least talking about cosmically recently formed, because they have lifetimes in a few tens of millions of years. So our hottest, most massive stars, they live hard, burn bright, and die young. Some people like to call them the rock stars of the universe because they live hard and burn bright, and then they die young. So I always like to anchor this into something that just makes you go, wow. So every current O star that you can find out there in our Milky Way galaxy formed after the dinosaurs went extinct 65 million years ago. So every O star formed after the dinosaurs went extinct. All right, so why do they have such short lifetimes? Let's reason this out. So the increased mass, these are the most massive stars. That means that their core temperatures are going to be really, 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 really high because gravity is squeezing everything together, driving up those core temperatures. And the higher core temperature means that the fusion reactions that are going on in the core can really, really proceed super rapidly. Higher temperature, higher fusion reaction rates. So even though that these more massive stars have more hydrogen to burn, the increased temperatures, which increase the fusion reaction rates to incredible rates, means that these stars burn through their fuel very, very, very fast. It's like trying to take a Hummer and drive it down the interstate at 120 miles an hour. You're not gonna, even though it might have an enormous tank, you're gonna run out of gas super fast. All right, let's go to the other end of the spectrum, the lowest mass stars out there. Let's go to an M-type star that has 1/10 the mass of the sun, a 0.1 solar mass M-type star. Figure out the main sequence lifetime. The main sequence lifetime is 10 billion years divided by the mass in solar masses, 0.1, raised to the 2.5 power. I get 3,162 billion years. That's 3.16 trillion years. The low mass M-type stars can last on the main sequence for trillions of years. So M and K type stars have dozens of billions for the K types to trillions of years for the M types. This is older than the 3.8 billion years age of the universe. So these stars, I'm not saying they're older than the universe because they were born after the universe, but they can live longer than the current age of the universe. So these stars are essentially eternal. They're going to keep shining as they are for many billions to trillions of years into the future. Many more already, how long the universe has been around, it can stick around for many times that length of time. That's incredible. So these stars are almost effectively eternal. They don't really die except after trillions of years. So, why do these stars live so long? They have only a little bit of mass, so you'd think not very much hydrogen. They should just burn out really quickly, right? You don't have very much fuel to work with, except the lower mass means lower core temperature. So the fusion reaction rates actually go at a very sluggish pace, meaning that they don't produce very much energy per second. Therefore, the stars have a low luminosity. So they are very, very slowly converting their hydrogen to helium. And even though they have a lower mass, the fact that they're fusing their hydrogen to helium so slowly means that they essentially can keep that they can they will very, very slowly convert that hydrogen to helium, making it take effectively forever for them to burn through all their hydrogen converted to helium in their cores. All right, so hopefully you enjoyed seeing how all of these properties came together, and we can now start unlocking even the lifetimes of the stars themselves. We can see how all these properties connect to one another. It's almost as if over so far in this unit 2 part 2 about the stars, we've unlocked the secrets of the stars themselves. We have a rhyme and a reason. We understand the stars. The only thing we haven't done is figured out how they are born and how they die. And that's going to be the majority of the rest of this course, is talking about the birth and death of the stars. All right. Thank you for tuning in. I'll see you in the